Magnetic fields. Electric field lines were used to show how electric charges would exert forces on other charges. We're going to use a similar concept here in magnetism. But what's nice about magnetic field lines is they are more easily seen, and I put that in quotes because you're really not seeing the lines. The above is a picture of iron filings. We have these little tiny pieces of iron, and we dropped them on top of a paper that was on top of a bar magnet. So let's see, can you see the magnet here? And we're saying this is the North Pole and this is the South Pole. All the magnetic filings line up in the direction of the field lines. Because iron is a magnetic material, it will act like little bar magnets in the presence of a magnetic field. They will align with the magnetic field of the large magnet. The field exits one end of the magnet, see, leaving here, and returns to the other end. And it comes back after going like this. We ran out of room on a little slide, but it goes something like this, and it comes back there. And also note, the field lines go through the center of the magnet, making a complete loop. Unlike electric field lines, if you remember there, I could have a plus charge here and a negative charge here, and the electric field line would just be that. It's a straight line. There's no complete loop. So we've shown how the blue line goes all the way around, completes outside the little picture. And then the red line here, that shows you a complete loop, leaving the magnet here, coming around, coming back in, and going back out. The key word here, or keywords, complete loops. Arbitrarily, which means we're going to use a convention here, somewhat like when Ben Franklin named the positive and negative charges, magnetic field lines are defined as leaving the north pole of the magnet. You can see how the arrows are coming out of the north pole and re-enter the south pole. The lines specify the direction that the north pole of another magnet in the field will point towards. So if I put a magnet here, which way is the North Pole going to orient itself? Well, the arrow is going this way, so the North Pole should point this way. This would be the North Pole. This would be the South Pole. If I put somebody over here, a magnet, the north would point in this direction, the same as the direction of the field. This would be the south. And again, these loops here that just look like they're going nowhere, they really go way out here and complete over here. We just ran out of room on the slide. Once again, all magnetic field lines form complete loops and go right through the magnet. Just like electric fields, different configurations of magnets will produce interesting magnetic fields. Here we have two north poles close to each other. We know they're going to repel. And look at these field lines. You can go back to the electric field unit and find out that that looks just like two positive charges nearby. And again, the arrow leaves the North Pole, just like in the positive charge, the arrows would go like that, the electric field lines. Well, obviously much prettier than that, but that's the general idea. So these two magnets are repelling each other. Now you might say, what about the lines inside? Well, hopefully you would have said that. Well, they're covered up by the colors here. But actually, the lines go all the way through. They make complete loops. Here's a picture of two magnets with their opposite poles next to each other. And you're going to ask, where are the complete loops here? Here I have leaving the North Pole, goes into the South Pole here. It's going to go through the South Pole. And let me pick up the pen again, then comes around like this and re-enters the South Pole and starts again. You have a complete loop. It just doesn't go from the north to the south and then stops. It has to go through the other magnet, come all the way around, and come out. Again, complete loops, and these two magnets attract each other, just like a plus and a minus charge would do.